Alright, so I'm talking about the concepts of stoichiometry, moles. So the first thing is a mole. What is a mole? Mole is basically, it's a way to count molecules. So I'm supposed to think as number of molecules. So commonly the number that we associate with a mole, 1 mole, is defined as 1 mole. It's equal to the number of carbon atoms in 12 grams of carbon. So the number of carbon in 12 grams of carbon. All right, so that number we define as Avogadro's number, which we call Avogadro's number. And Avogadro's number is, this is an important number, 6.022 times 10 to the 23. Right, so if you have 12 grams of carbon, then you're gonna have 6.022 times 10 to the 23 atoms of carbon in there. So when we think of 1 mole, just think of 6.022 times 10 to the 23. That's what 1 mole is. It's just a unit. So real quickly, just to read, being able to read the periodic table, just a reminder. So let's say we have some molecule. I'm just gonna say nitrogen, N. Then we'll have the number 7 here, and 14 here. And what this 14 here means is its atomic weight or mass. So we think of that as how many grams of the molecule there are in 1 mole. So this is mass. So we say 14 grams of nitrogen. That's how heavy it is for 1 mole. Which means that also means the same thing as we know that 1 mole is 6.022 times 10 to the 23. We know that means that 14 grams of nitrogen in is 6.022 times 10 to the 23 molecules of it. I'll call it a molecule even though it's an atom, just because you'll probably be dealing with molecules later. Molecules. Yes. All right. So that's just one of them. That's an example. Oh, and then the 7. This 7 just means how many protons there are. And just to review what protons are. Protons are positively charged parts of the atom that are in the nucleus. So if we think of nitrogen as a circle, as an atom, then in the middle you've got your protons, which are positively charged. So on here we got 7, so there should be 7. They should be uniform size, but I just drew them poorly. And then you've also got neutrons in the middle. And these are each weigh 1. They each weigh 1. So this would be 7 of the 14, and then the other 7 would be like neutral, 4, 5, 6, 7. 7. That's 7. And then on the outside would be electrons. But I don't think you really need to worry about that just yet. But there's gonna be like electrons, which are like negatively charged particles that will be orbiting it. So this is nucleus, and then that's what's orbiting it. All right. So I'm going to jump into the ideal gas law. I think this might end up being used. Hopefully, I don't think you have to learn just yet, but some questions will ask you for volume. So when a question asks you about volume, it's essentially asking you usually about a gas, and it wants to know how much space that gas is taking up. So we have something called the ideal gas law. Ideal gas law. And what the ideal gas law gives us is an equation that helps us determine one of like 4 variables based on what you currently have, and you can figure it out. So this law goes pressure times volume is equal to moles, which remember is a unit of how many molecules there are, based on its multiple of 6.022 times 10 to the 23. Number of moles multiplied by Planck's constant, which is just a number you'll learn. I'll define what it is, times temperature. And temperature is, in this case, measured in Kelvin, which I'm not sure you heard of. Kelvin is another unit of temperature we use in chemistry, and Kelvin is essentially equal to degrees Celsius plus 273.15. So Planck's constant, in case you're wondering, R equals 0.08206 times liters times ATM. ATM is it's called atmosphere, it's a unit of pressure, divided by Kelvin times mole. So, yeah, you basically just plug this in, but to find, they will give you most of these constants usually, and then you can find what the last one is based on that. So an important value to know is that for gases, at STP, which stands for standard pressure and volume, standard temperature and pressure. Standard temperature and pressure. So you're probably wondering what standard temperature and pressure is. So I'll define it. Standard temperature and pressure is 0 degrees Celsius, and the pressure is 1 atmosphere. So we can actually find out what the volume of 1 mole of something is at this given STP. So just plugging it into the equation, we have the pressure is 1 atm, so 1 atm. And writing units is really useful for these because it'll help you make sure you have nothing missing. Oh, there's a glint. P times V, we don't know V is yet, but V will be in liters. That will be the unit. And for moles, so we have 1 mole, right? We have 1 mole times R, 0.08206 liter ATM, all divided by Kelvin moles. P, V, and R times T. At 0 Celsius, remember that's Celsius, and we want it in Kelvin. So we got to add 273.15 to 0. So 273.15 Kelvin, right? So then we can multiply this out, and you get Kelvins cancel, the moles cancel, and you're going to get volume equals 0.08206 times 273.15. Can't forget our liters, ATM. Divide both sides by 1 ATM. 1 ATM. The ATMs cancel. The 1 goes to nowhere. So we're gonna have 0.00826 times 273.15 liters. And what that number is equal to is, I'm just gonna box it right here. 22.4 liters. So what that means is there are 22.4 liters of any given gas at STP for 1 mole. So when they ask you for the volume of your gas at STP, just calculate how many moles of the gas there are, and then multiply by 22.4, and that'll be the volume, how many liters of gas there is. Similarly, if they tell you the volume of your gas, say they tell you that you got like maybe, I don't know, like 50 liters of gas, then you're just going to divide that 50 liters of gas by 22.4, and that will give you how many moles of gas you have. And then you can continue to do your calculations. All right. So now we're going to go into like the idea of some of these questions, how they work. How to work out stoichiometry. what is stoichiometry? Stoichiometry is basically how we think of how we work with equations, because we need to make sure that every single equation is balanced, that the atoms yield the correct molecules. So when we think of that, we can't really use mass anymore because they're not the same weight, right? So I think of like, you can like think of like on like a small level, like, oh, you need like, instead of thinking of you need 15 grams of a banana, let's say to make your ideal banana shake, you need a cup of milk. You need a cup of milk, plus let's go have banana. And this gives you 1 banana shake. Right, so we're just think of the moles as like how many of these there are. So we could also say maybe 1 milk and two bananas creates 1 banana shake, right? So that would mean that 2 bananas is needed for 1 shake. So stoichiometry is similar. We're just using elements to really create this. So we can think of it like maybe you need, like let's say the creation of water, right? H2O. You need H2 plus O gives you H2O, right? You need one of H2, one H2, and 1 oxygen to make your water, H2O. Or you can alternatively think of this. 2 just H's plus 1 O also forms H2O, right? Because you got 2 H's here and then 1 O. So 2 moles of just singular hydrogen plus 1 mole of oxygen yields you 1 mole of H2O water. Got it? So 2 moles of this, 1 mole of this, 1 mole of that. 2 bananas, 1 milk, 1 milkshake. All right. With all this in mind, I'm going to try to throw everything together. I just want to remind real quickly that we know from the periodic table that for a given molecule, I'll make this bigger actually, it's small again. For a given molecule, a given atom, let's say, hydrogen. 1 proton, this, perfect job. This means there's 1 gram of it per mole. Okay, so we're gonna also think of this as, that means that 1 mole is there per 1 gram of just pure H. And we also think of this like, that means that there's, for 1 mole of H2, there's 2 grams now. Because it's the same number of atoms, but you've doubled the weight because you've got 2 hydrogens attached to each other. And that makes it 2 grams. All right, I'm gonna try doing some questions now. All right, first question. Oh, we also need to talk about limiting reactants and excess reactants and dimensional analysis. So limiting reactants are essentially what stops you from continuing to make more. So let's say that we had 40 bananas. We had 40 bananas. But we have only 1 cup of milk. Right? Then what's going to happen is you can't really make more than 1 milkshake because you've only got 1 cup of milk. So this would be our excess reactant because we're going to have leftover after we're done, and this will be our limiting reactant because we won't be able to. We use all of it, and it's what stops us from completing more reactions. So when you see in a question that they say you are reacting with an excess of hydrogen gas or of oxygen, just know that the other reactant is what's limiting it. That's the reactant that gets used all the way up to finish the reaction, and then there's going to be leftover of the other thing, but there's going to be leftover of your gas, but your other thing is going to be completely expended. There's going to be none of it left. All right. Bunch of 3 questions now. So I'm just going to do 3 questions real quickly. give you a feeling for it. So the first question I'll do is, what happens when you get, let's see, I need to actually open this. So this is the reaction we're working with. N2, nitrogen gas, plus 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields us, should be 2 moles of ammonia, 2 moles of NH3. So in case you're wondering, NH3 is ammonia. It's a type of gas. It smells really bad. It's what it smells when you pee and stuff. So the question asks, what volume of ammonia at STP is produced if 25 grams? So volume of NH3 at STP if 25 grams of nitrogen, I'm doing 50. If 50 grams of N2 is reacted with excess of H, is reacted with excess of H2, right? So the first thing to look at is, what does question want? The question wants to ask volume of a product, right? And then the second thing I notice is that it's at STP. And if you remember from earlier, what is STP? 0 Celsius, 1 ATM. And we're gonna use what we learned earlier, that STP, 1 mole of gas is equal to 22.4 liters. And now I'm gonna look at, okay, we have 50 grams of N2, right? And then we have excess H2. So instantly the first thing I know is that because it's excess H2 gas, hydrogen gas, I know that my limiting reactant is going to be this 50 grams of nitrogen gas, right? So now I want to convert this into moles because we can't react the weights. We have to react how many of each thing there are. So 50 grams of N2, right? 50 grams N2. And we know from the periodic table that the mass of just nitrogen per mole, that we know that nitrogen itself is 14 grams of it per mole, right? Which means that when we have 2 nitrogens attached to each other, that means that we have 28 grams per mole, right? We just added the 2 nitrogens together. We had the nitrogen and then the nitrogen to get us 2 nitrogen. So we're gonna add each weight, 14, 14, 28, right? So now I have 28 grams of nitrogen gas per mole. So that means that 1 mole of gas, 1 mole of N2 gas is equal to 28 grams. So this is a concept called dimensional analysis, where you try to match up the units together. So it's basically like trying to convert between inches and centimeters. This is a similar idea, except we're counting between number of molecules and its weight. So 50 grams of N2 gas, 1 mole of N equals 1 mole of N2 to 20 grams of nitrogen gas, and that will yield us 1.7857 moles of N2. All right, just check it out. If you need to pause at any point, you can pause. All right, so we have 1.7857 moles. So this is the first question that we've done, 1.7857 moles N2. Okay, now we know this is the limiting reactant, so we need to look at how many moles, no, don't. Okay, we're good. All right, we need to how many moles of N2 correspond to moles of ammonia. So we see that 1 mole of N2 produces 2 moles of NH3, right? This is like a one banana can make 2 shakes, right? You can split them up. So in this case, we have 1.7857 moles, a lot of moles. So 1.7857 moles of nitrogen gas we multiply it this time. So this yields, we get 2 moles of NH3 for every 1 mole of N2 that we use, right? So we get that, and that gives us 3.5. That's the ugliest speed I've ever written in my life. 3.5714 moles of NH3. Now, if you wanted to continue knowing the volume, then you want to multiply this. We have moles, right? This is our product. But we're not done because they asked us for the volume of NH3. So now we do, this is a gas. So we do 3.5714 moles of NH3 multiplied by 22.4 liters of gas corresponds to 1 mole. And I actually don't know what this number is. I didn't write it down. Give me 1 second. 22.4 times 3.5714. 3.5714. All right. Basically, you have 80 liters. Make sure to write what it is. 80 liters of NH3 yielded. That's for 50 grams of N2. With excess hydrogen gas. All right. I'm gonna kind of fly through this next one. And remember, I can only do that instantly because it's at standard temperature and pressure. Otherwise, I would have to plug it in to see. We can talk about ideal gas a little bit more later. All right, number 2. Gotta keep track of this. Number 2. Okay. And 5, KClO3, 2. Like potassium chlorate or something. All right. So if we have 5 grams of potassium chlorate, it's decomposed, what volume of oxygen is produced? So 5 grams of KClO3 product of O2, and they want this in volume. And this is at the standard temperature and pressure. Start seeing standard STP again. Just remember, STP, 1 mole of the gas is 22.4 liters of gas. So let's kick this question off. So quickly, our limiting reactants, obviously this is the only reactant. It's going to break apart. So we're going to have 5 grams of this. So what is 5 grams of KClO3 in moles, right? So we have to multiply this by some number. It should be the other way around. How many moles? 1 mole of this is equal to how heavy? We need to add up each of these individually. So how much is 1 mole of potassium? Potassium's weight is 39.1. So we have 1 potassium plus 1 Cl, which is chlorine, 35.45 plus 3 oxygens, right? So 3 times 16. So that's going to be, this is our molecular weight. It's how many grams of this molecule are available in 1 mole. So this number turns out to be 0.0408 moles of KClO3. So I just added this up already, and you should get 122.55 out of that. All right, so we have that many moles, right? Now we know how many moles of oxygen we have. So we know that 2 moles of potassium chlorate yields us 3 moles of oxygen gas, right? So I'm saying 2 moles of KClO3 gives us 3 moles of O2, right? So we need to convert our product, this amount of moles of KClO3 into moles of oxygen. So we have 0.0408 moles of KClO3 multiplied by, we get 3 moles of oxygen gas for every 2 moles of KClO3 we use. Right? That goes bad. And this will give us 0.0612 moles. Ooh. I'll write it again right here. It's fine. Equals 0.0612 moles of O2, right? So we're one step away now. We have how many moles of the gas there are. So now we just need to multiply this number by, remember the number, 22.4 liters of gas per mole, right? And this will give us 1.37 liters of O2 gas. Okay. Do one more. For this last one, I'm going to be doing, this is our equation. It's acid base. Na2SO4, probably. Na2SO4. Na2SO4. Alrighty. So this one's asking me how many molecules, right? How many molecules of probably H2O of water. Water is H2O, right? H2O are produced if 2 grams of sodium sulfate are produced. Produced. Right, so we have 2 grams of sodium sulfate. Sodium sulfate is this right here. We can know that's that because it's produced. So we're asking ourselves now, basically, we need to convert these into moles so that we can do a ratio to compare them, and then we need to convert that moles to molecules. So the first thing we're gonna do is convert our sodium sulfate into moles. So sodium sulfate is Na2SO4, right? So we have Na2SO4. So we need to find the molecular weight first. So we have 2 sodiums, right? 2 NAs in here, and NA's weight is 22.99. And then we need to add S, sulfur. S is 32.06. This is on your periodic table. Plus 4 oxygens, 4 times 16. And this should get us equal to 142.04 grams per mole of Na2SO4. Cool. So we know how many grams are in 1 mole of sodium sulfate. Now we just need to find out how many moles of sodium sulfate we produced. So we need to work backwards again. So we have 2 grams of it, right? 2 grams of Na2SO4. And we need to multiply that by 1 mole of Na2SO4 is the same as saying 142.04 grams of Na2SO4, right? So this means that we have how many moles of Na2SO4? You plug into your calculator, 2 divided by 142.04, and it gives us 0.01408 moles, right, of Na2SO4. And this is not the division sign, it's just the underline. Okay, so we have 0.01408. So I'm gonna write that down right here. 0.01408 mole of Na2SO4. Okay. So in our products, we can see from this reaction right here, we have an imaginary 1 right here, an imaginary 1 right here, right? You make 1 water for every 1 sodium sulfate you make, right? So they have a 1-to-1 ratio in their product in moles, which means that actually I've just completely finished this question. So 1 mole of water is produced for every single 1 mole of Na2SO4 that you produce, which means that you're yielding actually the exact same number of moles of water. So we have 0.01408 moles of water. All right, so what does that mean? That means that now they're asking us not how many moles of water we have, but how many molecules. And if you remember now that we have, so I'm gonna change this right here. This is now moles of H2O. I'm gonna erase this calculation, okay? So now we need to find out how many molecules. If you remember that Avogadro's number represents how many molecules there are in a mole, or how many, it represents how many, it's derived by how many molecules of carbon are in 1 mole, or in 12 grams, and we basically use that number to say how many molecules are there in a mole. So remember that. So we can also think of Avogadro as, Avogadro's number as molecules in 1 mole. Okay? So that means that basically it's molecules divided by moles. So we have, for water, we have 0.01408 moles of water. And we multiply that by Avogadro's number, 6.022 times 10 to the 23 molecules for 1 mole, right? And this is going to give us probably the number you're gonna first see. 8, 4, 7, 9 times. But I think you've probably learned scientific notation before, and they want you to have something in your ones place. So we can shift this to the left by increasing this one, decreasing this by 100. Multiply this by 100, divide this by 100 to make it equal, and we will get 8.479 times 10 to the 21 molecules. Ooh, I made a mistake. I need to write that down. Which is water, H2O, which is water. And that is our final answer. All right.